Greetings. This is a short lecture showing an example of test-driven development of a application designed to solve what's called the triangle problem. In 1979, Glenford Mayer wrote The Art of Software Testing. The Art of Software Testing was the first book dedicated to software testing that was ever published. In chapter 1 of the book, Mayers wrote the following text, and this is quoting directly from the book. Before beginning the book, it is strongly recommended that you take the following short test. The problem is the testing of the following program. The program reads 3 integer values from a card. The 3 values are interpreted as representing the lengths of the side of a triangle. The program prints a message that states whether the triangle is scalene, isosceles, or equilateral. And then Mayer writes, on a sheet of paper, write a set of test cases, i.e. specific sets of data, that you feel would adequately test this program. When you've completed this, turn the page over to analyze your tests. And Mayers talks about, in the book, at that point, about 14 different ways that you could test that application. Since then, in 1979, many people have developed courses, training material, techniques, methods to test various types of software on various technology platforms with various methods, tools, and techniques. And often they go back to Mayers and they take the triangle program and say, how would we use this technique with the triangle program? So the triangle program has become a very generic example used in all sorts of contexts to demonstrate software testing techniques. Now, what I have done here is working with some undergraduates from McGill University. I have asked for the creation of a triangle program, but instead of implementing them with an integrated development environment, I wanted them to be implemented with flowcharts. So the entire application is implemented progressively, one test at a time, using test-driven development, right? You create a failing test, you show it fails, then you write just enough code to make it pass, then you show it passes, then you make sure all the previous tests still pass, then you move to the next one and continue through it until you've exhausted your tests, and at the end you have a working application. So I asked for this to be created with flowcharts for a couple of reasons. One of the most important reasons was to be able to demonstrate to non-technical stakeholders on projects the value of the technique of test-driven development as a programming approach. So I want to show that. But also, I wanted to be able to do things like group activities and exercises where instead of writing code with IDEs, we build visual objects with flowcharts. And I've actually taken this and implemented it with Velcro and plasticized index cards on black felt mats where we can construct applications by drawing flowcharts on it and implementing TDD basically progressively, adding the different flowchart elements as we go. So I urge you to give it a try if you ever want to try to explain TDD to someone or to get used to solving problems with TDD. It's an excellent way to learn about TDD without having to worry about the nuance of a programming development environment. It's great for non-programmers to learn about TDD, test-driven development. Now, if I just move on here. So the first step in test-driven development that we took on this project was to brainstorm on unit testing ideas. And so we took this and we built a mind map. The map was actually made with the open source tool FreeMind. And there's a copy of that in the My Courses test-driven development directory. All these examples are there, including the flowcharts in both PDF format and Visio format, if you want to take a look at them. So in the brainstorming, we built this mind map, and we classified the types of error conditions as follows. So there's basically at the top of the list, counting the number of parameters, so too few, too many, the right number of parameters. For this, for a triangle, we expect 3 parameters representing the lengths of the 3 sides. We want the so how many parameters is one thing to test. The length of the input strings is another thing to test. So if you think about typing in a value for a numeric value, it's still text that you're typing in. There is a string length, and there may be an aggregate maximum and individual maximums for each of the 3 parameters. So that's the string length. Then we have parameter types and parameter value ranges. And then, of course, there's also the business logic, which is the different types of triangles. If we take a quick look at the parameter count, so we could have too few parameters, too many parameters, the correct number of parameters, no parameters, or way, way too many parameters. In fact, we didn't include the test way too many, but this would be something that might be of interest for security purposes. Hackers will very often put very large inputs into a small field to try to break the application and find ways into it with the buffer overflowing. The length of the strings, well, the aggregate length could be too long. The length of A could be too long. The length of B could be too long. The length of C could be too long. So those are the input string length test conditions. There's parameter type conditions. So we have 3 parameters, so length of side A, B, and C, if you will. They could all be wrong. So, for example, characters instead of numbers, text instead of numbers. So they could all be wrong, or they could all be right, none wrong. And if there's one wrong, it could be A wrong, B wrong, or C wrong. And if there's 2 wrongs, it could be A right, B right, or C right. So there's 3 permutations of the case of 1 wrong and 2 wrong, all of which would necessitate testing. We go from there to value ranges, and for value range test ideas, well, you look individually at A, B, and C, and A, B, or C could be too big or too small or in range. In our case, I believe we specified that it should be an integer between 1 and 100, so that was the constraint we put on the project, part of the requirements, if you will. And if it's too big, it could be a little bit too big or way too big. And the way too big would be to exercise things like precision, but also things like casting. If you're using a variable that's a 32-bit variable and you put a number that would require 64 bits, you would only be looking at the least significant part of it. So that would be way too big. And also way too small would be something that's, for example, got many digits after the decimal point. So we have too small, way too small, too big, way too big, and in range for A, B, and C. So those are values of parameters. Then we had the business rules of the triangle. So we have the valid isosceles, which could be 3 permutations. So isosceles means 2 sides of the same, one's different. So it could be A and B the same, A and C the same, and B and C the same. So there's 3 permutations of isosceles. There's scalene triangles. There's only one possibility of scalene triangle, which is A not equal to B, not equal to C, not equal to A. And there's also equilateral triangles, which is only one case, A equals B equals C. And all of these would have interesting tests in range or at the boundary. So this would be boundary tests at the minimums and maximums of each of the variables. So that would be for the business valid triangles, but there's also invalid triangles. It could be defined with the correct type and the correct value range, but still not make a triangle. For example, if you say A is 5, B is 5, and C is 20, well, there's no way that will make a triangle. So you basically have a law of the triangle, which suggests that the sum of 2 sides has got to be, I believe, greater than the third side. The sum of any 2 sides has to be greater than the third side. And in that case, you're following the rules of the triangle. That goes back to the ancient Greek models of math, the Cartesian math. Okay, so that's business logic. And every domain, by the way, has business logic. So this is the domain of geometry, computational geometry. And we start. So the first test here, and I'm not going to go through all tests, but I'll show you a few samples. So the first test was starting from a blank flowchart. So it just has a start and an end block. You'll see we try to do the case 2, 3, 5 and expect it to be not a triangle. 2, 3, 5 is a line segment. And when we go through this, the line showing the control flow path that we follow is in red to indicate that it fails. And so what we do is we add a little bit of code. That would be the flowchart element that says, okay, well, if A plus B is greater than C, then it's not a triangle. And now 2, 3, 5 gives not a triangle, and that's fine. That's a passing test case. So it's now we note that in green. Later on, we get to a point where we have a scenario where we have an isosceles triangle if the input is 2, 2, 3. And if we trace through the code at that time, we find that it gets to the end without saying that something is isosceles. So we have to add some code. We add a little bit of code here, and now the case is if B is equal to C, B is not equal to C, but A is equal to C, then we have isosceles in this particular case. If you follow the path, it works correctly. And after we make that change, of course, we also repeat all the previous tests that we've run. So we're showing they all still pass. So we walk through each path here in different colors to show that they still pass. A very tedious activity to go through. This is another case where someone types in 0.5, 0.5, 0.5 and expects an error message saying the values are out of range low. But if you trace through the code, it says, hey, that's equilateral. Now, of course, it looks like equilateral, except the value is too low. So we have to add a little bit of code to handle the case of number range being correct. And now when you type 0.5, 0.5, 0.5, you get an error message saying invalid input range. So we have basically cleaned up the case, the error handling with that test. And of course, we repeat all the previous tests. And if you look through them, we regress all these tests, all these paths. Every single time we add a little bit of code, we add an additional test and a little bit of code, we regress all of these unit tests. So we're always checking to make sure we didn't accidentally break something. Now, if you look at this code also, you'll see at the bottom, there's a line of code that's not executed by all this regression. This one little box at the bottom, A equals C, is not executed. And so what happens is in the end, what we do is we refactor the code, and we repeat the regression to make sure they all pass. So that's sort of at the end we do that. In the end, I believe it was about 20 test cases that were implemented, and all of these are demonstrated in the example directory step by step by step, and the flowcharts grow and grow and grow, and the regression paths get bigger and bigger and bigger. And in the end, you have quite a clean implementation of Glenford Mayer's triangle program from the art of software testing, implemented with flowcharts and test-driven development. Thank you for your time. I hope you enjoyed this example, and take care.